Good morning, good afternoon, or good evening, whenever you're taking a look at this video. So we're going to continue with hypothesis testing. And I want to do a little review with an example of what we left you with back at the introduction of hypothesis testing. And then today we're going to take a look at how to construct what's called a hypothesis test, the experiment, and come to a conclusion. And then what do we do with that conclusion? So as you can see in this one, I'll just read through it for you, that we're going to suppose that you personally, or me, are a researcher for a pharmaceutical research company, and you're investigating in the side effects of a new cholesterol lowering medication, and you want to determine whether the medication will in fact decrease the average systolic blood pressure level from the current population average of 110. So basically what this says is they've got data that the current average of all, you see mu, the blood pressure level currently is 110, and they want to see if they can come up with medication because it's still a little high, and they want to try to decrease that. And so they've got a new medicine. Now, why would they just give it if they haven't tested it? So they're going to take a sample, as you can see. They want to give a warning to be given not to prescribe the new medication whose blood pressure is already low. So they want to make sure that they're doing the right thing. And so to determine which of these hypotheses is correct, they're going to take a sample of randomly selected patients. Of course, they don't want it biased, so they're going to select it. We've talked about 5 different sampling techniques in our particular class. There are others out there, but you want to randomly select patients who are currently taking the medication and want to record their blood pressure levels and calculate the average blood pressure of those people that they took a sample of. That's why you see the X bar is the sample average. And they want to get the sample standard deviation as well, little s. And most likely, the average sample of patients' systolic blood pressure levels will not be equal to exactly the 110. Most likely, it's not going to be that way. It's going to be either higher or lower, likely, even if the null hypothesis is true. Now, suppose that the sample average blood pressure X bar is less than the hypothesized mean of 110. Now, the hypothesized mean is that it's exactly 110. That's where the null hypothesis, the H sub naught, is going to come into play. And as we talked about it before, the null hypothesis will always have the equal. It's what's assumed to be true. So suppose that the sample average blood pressure is less than the hypothesized. Is that difference due to the chance variation, or is it evidence of a side effect of the cholesterol medication? That's the question we want to pose. So let's take a look and see what we're going to do with problems like that coming up in what I call chapter, for us, for the textbook we're using, chapter 9, section 2, and maybe even section 3. We'll combine those two today. So let me bring up and give you an overview of what we're going to be looking at, a couple different methods. Let me share my screen again. So this is what we did the other time, taking a look at some of the problems on how to set up a hypothesis test. And notice that we've got 2 new symbols, H sub naught and H sub A. And mu is the population average that we're looking at. And later on, we're going to be looking at proportions as well. But right now, it's the means. And the way I'm going to show you is this is always the complement of that symbol. So the symbols are going to be complements. The textbook, the author, and probably even most statisticians would say it's good enough just to have equal there. All of these could be equal sign. And it'll still, well, of course, that one is. That's the complement of that symbol. But all of these, it's good enough just to have equal. These guys, no way is it going to have an equal sign next to it. That's just the way we're going to set it up. We accept it. Okay, so taking a look at what the next section we're going to be looking at, there are methods of deciding the conclusion on this. And so we're going to be looking at the mean, sigma, if it's known or if it's unknown, and then there's proportions. So there's three different concepts, just like in confidence intervals. You've got sigma that's known, and it sounds like a Z test or a Z interval there if it was confidence intervals. Sigma not known, that means the only thing you have is either the X bar and the S, so that's going to be a T of some sort. And then there's the proportion. And there's two methods I'm going to show you. There's the critical value method, which is the bell-shaped curve that you're familiar with taking a look at earlier on. So that will look familiar. And then there's this new one called the p-value method, which is a straightforward method that you're just going to look at a number. The calculator is going to generate this number. Look at the number and compare it against something else and make a decision. This one is very visual. This one's not, in my opinion. Now, in the critical value method, as you can see what here, the steps that we're going to do, we're going to write out the null hypothesis and the alternate hypothesis. That's the two statements that you get, the H sub naught and H sub A with the inequalities. That's the statements that I'm talking about. With the critical value method, we're going to draw a picture. We're going to identify what's called the alpha. Now, the alpha, in your definition at the back of your packet, you would read that it's the area in the tails. When I say the tails, if it's a bell-shaped curve and you have, let's see, symmetric, of course, bell-shaped curve is symmetric, and you've got two different tails because you're shading in between. So you've got two tails. The alpha is the sum of those two tails. If it's one tail, that is what the alpha, and it's the area in the tails or the probability. Critical value, we're going to find a critical number, which I'm going to show you what that is and how to find that. And we're going to place that on a number line. And we're going to shade some kind of area. And I'll show you what that is. It's called the rejection region. And we're going to also find a test statistic. I'll show you what that is. And you're going to make take an observation and see if that test statistic, this number, sits in what's the shaded region or doesn't sit in the shaded region. So shaded region is going to be rejection. Unshaded regions don't reject. And then at the end, we're going to summarize our results. Now, in the p-value method that we'll learn about, p-value method, we're going to find this by using our technology. And I'll show you how to do that with your calculator today. And there are a number of ways of making the determination. Basically, this is the best thing to do. Take a look at it. You get a p-value and the alpha. Now, the alpha is something that's predetermined. And I'll show you what those are. And if you remember our table that we used for confidence intervals, and if you remember that alpha divided by 2 was part of that symbol, z sub alpha divided by 2, or the t sub alpha divided by 2. So you're going to see that there's an alpha at the top of your table, and we're going to be taking a look at that too. So this is a way of making a decision based on knowing what the alpha you start with, and the p-value that's generated from your problem. Now, in the first part we're going to be looking at is testing about an average where you know your sigma. So sigma is given somehow. And this would be a situation that's unusual set of circumstances that would allow us to know sigma without knowing what the mu is. It's very, very unusual. The example used for this would involve cases that are less realistic than when alpha is unknown. That should be a sigma, my mistake, when sigma is unknown. So change that alpha to a sigma. That's a typo there. So in the one sigma is known, of course, we're going to know sigma is known. We're going to sample from a random sample. And this should look familiar. When I say familiar, in the past, you've had a z-score formula. In the past, it would have looked something like, very simple, z is equal to x bar minus mu all over sigma. And even sigma divided by square root of n, when it came up to the sample size, was more than 1. This note, symbol, mu sub naught, is your given average that you'll take a look at in the word problems. The p-values are going to be found by the calculator. The critical values we're going to get from the table. And we're going to either use the formula that's up here, or better yet, use the calculator. And that's the best way to do it. So that's what I'll do is calculator, calculator, nice. And this one here, we will have to use the table D, and I'll show you how to do it. Later on, I'll come back to this table or this page, because this is examples when you don't know sigma. Then notice we're going to use a T, but we'll come back to this later and check these. And then we are going to have to look at proportions eventually, and this looks familiar. So does this. A lot of these things look familiar to you, but now we're under the concept of hypothesis testing. All right, so we'll come back to these when we get to examples that are needing that. Okay, here's your first example. Now, what I want to do is, when I'm saying it's even a z-test, that means sigma's not known. That should mean that, excuse me, sigma is known. Sigma is known if I use a z-test. So this one should be out of a 9.2. We'll take a look and see how this works. So I want to state the hypothesis first. All right, let's read the word problem. Interested whether the population, mu, population average per capita annual expenditures on healthcare have increased. That's a key phrase right there, increased. Now, the symbol for increase is going to be looking like greater than. That's increase, no equal sign. We're interested in see if it's increased since years ago, 2007, currently. When back in 2007, the amount was $6,096. So in this case, we're going to select 100 Americans, randomly selected. That means N is equal to 100. And their 100, for the 100, their average healthcare expenditures currently is $8,000. Well, good grief, that looks like it's increased, hasn't it? But it could have just been an anomaly, because remember, this isn't all of them. This is just the 100. So this right here would be X bar is equal to $8,000. And research has shown that a standard deviation of 1,600. Now, here's a key, in my opinion, in the textbook, which kind of makes sense, that it's all about sentence structure. You see the standard deviation right here? That is its own sentence. This is your population standard deviation. If the standard deviation was intended for the 100, it should be included in the same sentence as the 8,000, indicating it's part of the sample. But because this is beyond the sentence, it's in its own sentence, then that's your sigma. Sigma is equal to 1,600. Now, alpha. Think of it as like confidence intervals as an example. Let's see, 99% confident, pretty confident, that's good. Let's see, if it's 99%, I'm 1% unconfident, or I'm 1%, it's a chance that I could be wrong. If I went 90% confident, it would be 10%. Now I take those percentage, the part that I'm wrong, and I take 1%, there it is. That's 0.01. So this has something related to confidence intervals in terms of the leftover. And you'll see that in our table in a second. So you pick, in this case, they're telling you this is the level they want you to use. So it's like, let's be 99% confident about this. And we also have to make sure that we can move forward. So remember, if it doesn't say normal, we have to make sure the sample size is big enough. And sure enough, n is big enough, it's bigger than 30. So now the next thing is, I want to state the hypothesis. And that's where your H sub naught and your H sub A comes in. And you're looking at the population mean. So now it's symbols. You know this is going to be an equal sign, and you can always put an equal if you wanted to. I'm going to look at the symbol that I'm considering or curious about. It's a greater than. It's got to go here with the alternate because it's got no equal sign. It has to go here. This one is the reverse, the complement, or as I said, the textbook will just use an equal always on that. And the value put right here is what you're comparing it against. Wants to know if it's has increased since $6,096 back in 2007. So that's stating the hypothesis. Now the Z data can be found by that formula, and the p-value can be found, well, will be found actually by using your calculator. So this could be by the formula or it can be by the calculator. So both of these are going to be calculator for me, for us. This one here, we're going to have to use a table, and I'll show you that. It's called the critical value for that we're going to be needing, which is the same as the test statistic, critical value test statistic. Spell that right. Statistic. There, that's better. And I'm going to do the first way I'm going to do is the bell-shaped curve. Okay, so let's get these numbers, and I'm going to show you with your calculator where to find this. The keystrokes here are in your packet. Those of you that purchased that packet of mine, and the back it gives you keystrokes as well as the textbook too. You can find it there. Where to find this hypothesis test. And gosh, it sounds like test, doesn't it? Remember I got stat tests is where you found the intervals, the confidence intervals, the same place where you find what's called a test. And there it is, number one, the Z-test. Number one, the Z-test. So hit that. And now the question is, do you have raw data, which I don't. Therefore, I've got statistics, so I'm going to hit statistics. It gives you prompts. Now, mu sub naught, basically it's the given population average that you have, which is this one here, mu sub naught. That's your mu sub naught. So for us, we're going to put in 60996. Sigma was already given. Remember that? Sigma was over here, 1600. X bar was given to be 8,000. Sample size is 100. All right, now look at what we have right here. Basically, you're making a choice between three things. Look at the inequality, and it's based on the alternate hypothesis. The inequality that you see there is based on the alternate hypothesis symbol right here. So I'm going to pick the greater than, which is that one way over there. And then let's do the calculation. Just hit calculation, and we're going to write down a few numbers. So the few numbers I want you to write down is Z equals 11.9. P equals, well, that's crazy, isn't it? Remember that scientific notation, take the decimal, move it to the left 33 times. That's basically 0. Okay, pull this away. Now, here's what you're going to do. You're going to take a bell-shaped curve that looks like this. Since we're talking z-scores, this is always 0 right here. Since you're talking z-scores, it's always 0 right there. You always have 1, 2, 3, -1, -2, -3, as you know. If this is a z-score right here, that's going to be way out in the right-hand side. Way over here is 11.9, because remember this is 3. This right here, since it's greater than, you're shading shade right. You shade right to what? Or compare to what? Right here. You shade right to the z-score. This is called your rejection region. Okay, so now what? Well, I want to find this critical number. I want to find this is from table D. Here's your table D. And before we looked at confidence intervals or levels. Now look at the next two rows. You see it says area and one tail, area and two tails. So let me tell you what's one tail and two tails. This is one tail because that's what I'm shading right. If there was a less than on this one, that's a shade left. And if there was an equal sign, not equal sign, that's shading both ends. So I'll just write this over here. These two are one tails. This one is two tail. One tail and two tail in terms of the shading. Well, on the table, what you want to do, since I've got one tail, look at one tail, area and one tail, and look at your alpha. Now, I have to go back and see what they told you. Oh, they told you want the alpha level to be 0.01. Here's the alpha level in 0.01. I wrote alphas to the left side of your table. They didn't, but that's basically, it's helpful. 0.01. And because it's a Z, Z's are always found at the bottom of this table, all the way down at the end. 2.326 right here. 2.326 right here. So now I found that critical number, and you're going to take a look and place where 2.326 sits on this number line. And as you can see, it sits right about there. This is don't reject region. And this is yes, reject. Yes, reject the region. And now you're going to say, well, what am I rejecting? It's all based on the null. So whatever your decision is, if we say reject the null or don't reject the null, because this number sits in the don't reject the null or don't reject region, that's your statement right now. So conclusion. Don't reject the null hypothesis, or H sub naught. You could have used that one, or even sometimes we just say just don't reject the null, period. We don't have to have the full hypothesis in there. All right, so now what's that telling me, or telling us? Okay. Don't reject the null hypothesis says we're not going to so now what have we got here? We've got the values of Z that we came from a calculator, and we got this p-value, which we're going to figure out what to do with that down the road. You draw your bell-shaped curve, and you know that right there in the middle, because we're talking about Z's, right there in the middle is going to be 0. And this is a 1, and that's a 2. That's a -1, -2, and -3. You know that. So now we want to find a critical number. So I'm back over here. We found the data value, found the p-value from the calculator. Find the critical number. Okay, the critical number comes from the table. And so I want to find the critical number from the table. And what I'm going to do is I'm going to take a look at the table right here. How you're going to take a look at the table is you look at the alphas that I put over here, 1 tail versus 2 tails. Now, this is a 1 tail right here. 1 tail because you're shading to the right, 1 tail. Matter of fact, if you see right here, 1 tails are always these inequalities, which is always in the alternate hypothesis. So, and then a 2 tails would be a not equal sign. That's a 1 tail. So what I'm going to do is I'm going to take a look at my table, look at 1 tail. I'm looking for 0.01, that's your alpha that was given to you. And because it's a Z, you go all the way down at the end, all the way down at the bottom, and there's your 2.326 that we're going to write down. That's called the critical number. 2.326. .326, and that's sitting right there. So what you're going to do is put in ... or solid line, doesn't matter, and you're going to shade to the right because it says greater than, shade to the right. And this is called your rejection region. Shaded region is always rejection region. This is, sometimes they say fail or don't. Reject region. So what you're going to do is look at your number that we come up with the calculator and just determine whether it sits over here or over there. 11.9 sits over here on the right hand side, way over here. So it's like we strongly reject something. We strongly reject. And it's all based on the null. So what you're doing is you're trying to determine whether you reject or don't reject the null. In this case, because that number right there sits in the way on the right hand side, strong rejection, then I reject the null hypothesis, and then we're going to end up having a statement at the end that we want to call a conclusion. Now, if I reject this, then I'm embracing this. That's the word I use. Reject this, I'm embracing this. Which indicates to me it looks like there's enough evidence and strong evidence because look at the $8,000. Look how much more that it is than that one. Isn't 8,000 more? That's the sample. So that means the average out there should be definitely more than $6,096 based on the sample and the information that I had. So what I'm going to do is I'm going to write a conclusion. We reject the null. There is enough evidence or sample evidence, just like maybe in the jury duty, there's enough evidence to say guilty or not guilty. Sample evidence to determine that oh my gosh, I can't even write that. The average, let's see, this would be average per capita annual expenditures. This is the big wordy sentence that we end up having. Expenditures on healthcare is more than in 2007, which was more than $6,096. It's increased. Definitely it's increased. So that's your, so far, your introduction to 9.2. There's going to be a part 2 with 9.2 and 9.3 coming up. And yeah, these are big problems, but we want to be able to have a way of solving these. So we're going to take a look at more of these examples and then take a look at the p-value method as well, which is less work, but come to the same conclusion. Okay, until next time, be safe.